I have a vector calculus midterm next week, so just as a way to study, I'm gonna be going over the content on that midterm. So first thing that I know is gonna be on the midterm is surface parameterization. Basically, this topic, you're just learning how to write surfaces as a parametric equation. So so right here, we've got a surface that's written as a function of x. It's a function of x in terms of x and y. So basically what I'm going to do is I'm going to rewrite it so that it's the vector r as a function of x, which should be a function of two variables. Let's just say u and v in this case, y in terms of u, v, and z in terms of u and v. So what I'm going to do first is I'm going to substitute x and r, or like x and y, as r cos theta and r sine theta because of how because of how the surface that I'm trying to parameterize looks like. It's a cone, it's relatively circular, so I'm going to go with this parameterization. So right now we've already established that x is equal to r cos theta, and that y is equal to r sine theta. And the last thing I'm going to do is I'm going to substitute the x and y terms in my z function so that I have my surface written entirely in terms of r and theta. So the x squared just becomes r squared cos squared theta, and the y squared becomes r squared sine squared theta. Now what I'm going to do is I'm going to factor out the r squared so that I have cosine squared and the sine squared term isolated. So we all know that this should be equal to 1. So I'm just going to take it out of my radical. And the square root of r underneath a radical is just r. So z is equal to r in this case. That means I can write my parametric equation as the vector r equals r cos theta, r sine theta, and r. Now I still have to do one more thing. I have to write down my limits. So based on this inequality, we know that z goes from 0 to 5. And because z is equal to r, that means that r must also go from 0 to 5. Another way to look at this is by asking yourself, okay, what's the lowest r value and what's the highest r value for this that corresponds to the surface? So down here, r is equal to 0 because the farthest point is at a distance 0 from the center. But up here, okay, that should be 5. So up here at the top of the cone, the farthest point on the surface is at a distance 5 from the center. So r must be 5. So that means that r just goes from 0 to 5. And the way that theta is measured for the surface is it's just the angle between like a given vector and the x-axis. So this cone revolves entirely around the z-axis. So theta just goes from 0 to 2 theta. And that is our surface. Now I'm gonna do another example that's slightly different and not as straightforward as this one so that everyone gets this. Okay, so this is another surface, but this time we can't easily substitute x as r cos theta and y as r sine theta because the surface isn't circular, and the limits are going to be a little more. We'll have to work a little more to figure out what the limits are in this just for this surface. So what I'm gonna do for this surface is I'm gonna keep x as x. I'm gonna keep y as y. And now I'm gonna isolate z so that I can have it as a function of x and y. So I'm just gonna move all the terms. Just gonna move everything to the right. And then multiply both sides by 10. So that I have something that looks like this. We can always simplify if we want. Okay, so now I have x written as a function of x and y written as a function of x and y, and z written as a function of x and y. So I can easily write my vector, or my parametric equation, as x, y, 10 minus 10x divided by 3 minus 5 over 2y. Now the limits. What are the limits? So I guess an easy way to figure out what the limits are, like to easily figure out what the limits are, you could sort of compare this to triple integration if you've ever done that before. So y should go from this. Yeah, so like the limits for this parametric equation should be similar to the limits that you would establish if you're trying to set up a triple integral to find out what the volume is underneath the surface and the xy plane. So if you were actually trying to find the volume underneath this surface and the xy plane, your triple integral, I'm just going to start with dz, dy, dx. So your triple integral is going to look something like 0. Like your first integral is going to be from 0 to the top surface, and then y is going to go from this to this curve. So the bottom curve is just 0, and the top curve should just be that surface evaluated at z equals 0. So x over 3 plus y over 4 equals 1, which is just 1 minus x over 3. So y is equal to 4 minus 4 over 3x. So then that would be the top curve for your dy integral. And then x would just go from 0 to 3. So this is the triple integral that you would set up if you're trying to figure out what the volume is underneath, or what the volume is in between this surface right here and the xy plane, like in this quadrant that we're looking at. So your limits would be the same. Essentially, they would be the same as this triple integral. So y would go from 0 to the curve 4 minus 4 over 3x. And x would go from 0 to 3. So yeah, as just to summarize what we did today, we looked at two examples of surface parameterization. The first one, where we've decided to substitute x as r cos theta and y as r sine theta, and then plug those values into our function our z function, which is in terms of x and y, and write that as a parametric equation. This strategy is typically good for circular surfaces, just like the cone that I have drawn here. And on the second example, we looked at a surface that isn't so circular, so we had to switch up our strategy a little. Basically, what we did was we kept x as x, y as y, and we wrote z as a function of x and y, and then threw those into our parametric equation, and we ended up with this. So yeah, that concludes today's video. Seems like I understand surface parameterization. Should be doing well. Should be fine on this final. I hope. Okay, bye everyone.